Welcome back, and the subject of today's video is going to be a demonstration of how to calculate a standard enthalpy of formation for a particular reaction from tabulated delta H of formation data. Now let's go back and quickly review from the last video what we mean by a delta H standard state of formation. Alright, so the rule there is that we're talking about the delta H associated with the formation of 1 mole of a substance. Typically this is going to be a compound, alright, made from its elements in their most stable elemental forms under standard state conditions. Alright, so let's do an example of this. We wanted, for example, calculate a delta H standard state of formation of this iron oxide that we have here. I believe that is going to be iron 3 oxide that we've got. What we can do is make 1 mole of that iron 3 oxide here. Okay, it's going to be a solid under the conditions of standard state. That's 1 atmosphere and 25 degrees Celsius. So that's a solid. All right. So in order to make 1 mole of that solid, we have to have 2 moles of solid iron combining with 3/2 of a mole of O2. Again, the iron is going to be a solid under standard state conditions. The oxygen obviously will be a gas under standard state conditions. And these things will combine to make my 1 mole of the iron 3 oxide in the solid state. Now, there's going to be a delta H standard state of formation for that. And that then turns out to be a value of minus 824.2 kilojoules per mole. So where did that number come from? Well, as it turns out, these are all tabulated values. So for pretty much any compound that you can think of as it exists under standard state conditions, we can look up a delta H of formation for that particular compound. So where is this data? Well, this data comes from thermodynamic tables that are found in your textbook, specifically between pages 1231 and 1244. So you guys can look at those tables and find examples of these values of delta H of formation. So the long and the short of it is we can go look these up and then use them. All right? So once I've got the delta H of formation, or I have access to them, what are we going to do with them? Well, what we want to do, as I mentioned here, is to calculate a delta H standard state for a general reaction using these delta H of formation values for the various compounds or elements involved. So let's look at an example of how we would calculate a delta H naught of reaction. So let's just pick a reaction. So here's a reaction that we can look at. We can have 4 manganese getting together with 3 oxygens, O2s here, to make 2 of these manganese oxides that we have. Okay? That's one form of manganese oxide that we can have. That one looks like it's going to be manganese 3 oxide, I believe. Now, in order to calculate a delta H of reaction for the reaction as I've written it here with these particular coefficients, I have to go to the tables first, and I have to look up these delta H standard state values of formation. Okay, so I did that. Now, for any element in its elemental form as it exists under standard state conditions, the delta H of formation will be 0. So solid manganese is how manganese exists under standard state conditions, so it's 0 kilojoules per mole. Oxygen, O2, that's how oxygen naturally exists under standard state conditions. It's oxygen, O2 in the gaseous form. So it also is going to have a value of 0 kilojoules per mole. So for any element as it exists in its standard state form under standard state conditions, that value of delta H of formation is going to always be 0. Now, for a compound, however, we're going to have a non-zero delta H of formation. So I looked up the delta H of formation for this compound in the table, and I got a value of minus 958.97 kilojoules per mole. So you guys can go to the table and actually verify that. You could also verify these values as well. They'll also show up in the tables. Okay, so once I have those values of delta H standard state of formation, what do I do with them? So essentially, I'm going to give you a nice little equation that works all the time. This equation is actually a permutation of Hess's law. So we could actually apply Hess's law to this as we did in class, and we could come up with exactly the same answers. But this is sort of a shortened version of Hess's law for this particular application, and it works all the time. All right? So if I want to calculate a delta H of reaction standard state that's going to be the summation of n times the delta H of formation of all the products. So this is a summation sign. So it means I'm going to sum up all of the delta H formations for all the products that I have, and each one is going to have its stoichiometric coefficient in front of it. So n corresponds to the coefficient of that particular compound as it shows up in the equation. So for example, in my case, I have 2 Mn2O3. So if I'm referring to this particular delta H of reaction, I have to have an n of 2 in front of it. And then I'm going to subtract from that the same quantity with respect to the reactants. So let's do it for our particular application here, for our particular reaction that we're interested in. All right? So here's my reaction. I've got all my delta H of formation standard state values. All I got to do is plug them into this equation. So starting out with the products first. So in the brackets here, N, 2 moles of MnO3. So there's my 2, which corresponds to the 2 stoichiometric coefficient up front here. Now multiply that by the minus 958.97. That's my delta H of formation for the manganese oxide. All right? And then what I'm going to do is set up another set of brackets to account for the reactants here. So here I have 2 reactants. This is truly a summation now. So I've got 4 moles of the manganese at 0 kilojoules per mole. And I got to add to that 3 moles of the oxygen also at 0 kilojoules per mole. So it's easy to see that when you do the math here, you're going to get 0 kilojoules out of this. Okay? On this side, you're going to get twice minus 958.97. So when you actually work the math out here with this particular species, because there's nothing over on the other side of the negative sign there, I'm going to get a minus 1917.94 kilojoules. Now I'm not going to call it kilojoules per mole. I'm going to just leave it as kilojoules because that's the kilojoules of heat that's generated by this reaction as I have written it. Okay? So that's how we calculated delta H of reaction for any reaction that we can possibly think of. So we'll practice this a little bit more on Monday. So we'll see you then.